Okay, on this video, we're going to talk about simplifying radicals. On the last video, we saw how radicals are really fractional exponents. And now we'll focus more on just writing them in radical form. Now, simplifying is sort of a subjective word. So what we mean by simplifying a radical, just a square root or a cube root of a number, is we want to have no perfect squares inside the square root, or no perfect cubes inside a cube root, no perfect fourth powers inside a fourth root, etc. And I've been teaching a long time and finally started to question, why do we really want to simplify radicals? I mean, this is something that's very, very common, but in some cases, you know, simplifying it can actually make it less simple in a way. For example, the square root of 63. If I had to estimate what that was without a calculator, think about what number is close to 63 that has a nice square root. And you probably realize, well, if the square root of 64 is exactly equal to 8, the square root of 63 is, not a little bit less than 8, maybe 7.9. I don't know exactly, but it's not too hard to look at that and get a nice numerical estimate of what the square root of 63 is. But you'll see after we simplify it, you might find it's a little bit harder to estimate that its square root of 63 is about 7.9. Nevertheless, we still need to learn this, and there is actually a good reason for why we sometimes want radicals in simplest form. So how we do this, so 63, notice 63 is made up of 9 times 7, and 9 is 3 squared. And that's the idea. We don't want any perfect square factors inside a square root. Now, what we can do, remembering that this is the same as 3 squared times 7 to the 1/2. And remember, one of our properties of exponents is I can essentially distribute to both of these. So I could make this 3 squared to the 1/2 times 7 to the 1/2, and 3 squared to the 1/2 would just be 3, and the square 7 to the 1/2 is the same as root 7. So that's essentially what we're doing, except you don't usually need to change it into fractional exponents. But what that is telling us we can do is that if I've got a square root of 3 squared times 7, I can essentially pull out the square root of 3 squared as 3 and leave the 7 inside. So the simplified form of root 63 is 3 root 7. Remember, that's 3 times the square root of 7. Now go back to my original question. How many people would have a harder time if I said, estimate what 3 root 7 is as a decimal, coming up with about 7.9? I know I would. And here is the truth. When you get to calculus, if you leave an answer as the square root of 63, by and large, most teachers aren't going to care. It's fine. We know that could be written as 3 root 7. However, for things like the placement test that some of you are going to take, you should probably still know how to reduce radicals, simplify radicals down, because if an answer was square root of 63, they would probably have it written like this. So you need to know that that's how you can simplify it. Okay, so let's keep going. So square root of 48, what I'm looking for are perfect square factors. Sometimes it's not obvious, and so what you can do is break them down. 48 is 2 times 24. 24 is 2 times 12. 12 is 2 times 6, and 6 is 2 times 3. So with square roots, I'm looking for perfect squares. So anytime so that means 48 is 2 times 2 times 2 times 2 times 3. I've got a pair of 2's right here, so I could write that as 2 squared. Another pair of 2's right there, so I could write that as another 2 squared, and then I have a lonely 3 here. And so anytime we can get a square root of something squared, that can be pulled out as a 2. This can be pulled out as a 2. It's going to get multiplied, and the square root of 3 stays inside. 2 times 2 gives me 4 root 3. Now, some of you may have realized that one thing I could also do is 2 times 2 is really 4, and there's another 4. So I could have rewritten this as the square root of 4 squared times 3 and got directly to 4 root 3 a little bit faster, and that's fine too. So ideally, you're looking for the biggest perfect square in there, but if you need to break it up into a couple of twos, that's fine too. You're going to get the right answer. Now, what about a cube root of 48? Now what I would be looking for is perfect cubes. We've already broken down 48, and we know that 48, well, I'll just write it in here, is 2 times 2 times 2 times 2 times 3, 2 times 2 times 2 times 2 times 3. And so what I'd be looking for is a perfect cube. So if I take 3 of those cubes, this is going to be the cube root of 2 cubed times, I'm not going to get any more perfect cubes there, so usually we just multiply that back together, make that a 6. The cube root of 2 cubed, that's going to come out as a 2. And we'll just have 2 times the cube root of 6 is the simplified form for that cube root. Most of the time we'll be working with square roots and cube roots, but just to show you the process, what if it was a 4th root? Then I would be looking for perfect powers of 4, and since 48 we've broken down already as 4 2's multiplied together times a 3, we could write this, whoops, that's the 4th root, as the 4th root of 2 to the 4th times 3. 4th root of 2 to the 4th comes out as a 2, so we end up with 2 times the 4th root of 3. By and large, like I said, most of the time we'll be working with square roots and cube roots, so maybe take a minute to see if you can break down the square root of 72. Okay. Again, you might see the biggest perfect square right away, but if you don't, you can always, that's an even number, so you could divide it by 2, that's 36. And maybe right here, I mean, you can keep breaking down 36, but if you just go 6 times 6, you've got a perfect square right there. And there's no need to break that down any further. So I could write this as the square root of 6 squared times 2. So that becomes 6 root 2. Okay. Yeah, so like I said, I mean, when you get to calculus, nobody cares about simplifying square roots, and it seems sort of illogical to simplify square roots when you can easily estimate the square root of 63 versus this. But there is a reason why you want to sometimes simplify radicals, and that is when we want to add radicals. Because if I want to add the square root of 72 plus the square root of 24 plus the square root of 18, what I will tell you is this is not equal to the square root of 72. You can't put them together and just add these together. That is not true. You can try it out on a calculator if you want. You'll see that that's not true. But what I can do is if I break these down into a simplified form, we already did this one. This one was 6 squared times 2. So this one is 6 root 2. This is 6 root 2. We just did that one. Now let's think about 24. 24, if I broke that down, is 4 times 6. And 4 is a perfect square. And 6 only has 2 and 3, which is not a perfect square. So I could let's take an intermediate step. I could write the square root of 24 as, you could write that as 2 squared, or you could even just do this, 4 times 6. For 18, thinking of perfect squares, that is 9 times 2. Okay, this one we already simplified. That is 6 root 2. And then you just argue this, like that's 2 squared, but you can pull that out. In other words, the square root of 4 is 2. So that is 2 root 6. 9 is 3 squared, so the square root of that is going to be 3. That comes out, that is 3 root 2. And then when you add radicals, it's kind of like with polynomials. You can only add radicals that are like terms, and they have to be the same multiple of the same root. In other words, 6 root 2 plus 3 root 2, just like if I said, what is 6x plus 3x, we can combine those together. That is 9x, because we have the same root 2. But I cannot combine this one because it has a different root. It's a different radical. But I can combine these two. So the best I could do with this is say this becomes 9 root 2 plus 2 root 6, and that's as far as we can go. You can do the same thing with cube roots. If you wanted to add 2 cube roots, you can't just add these numbers together and take the cube root, but we can see if they have any common radicals. So we'll break this down. We're looking for perfect cubes, perfect cubes. 16 is 8 times 2. 8 times 2, and remember 8 is 2 cubed times 2. So I'll just do this. If I wrote it as a cube root, then I can pull that out. This is going to be 2 times the cube root of 2. I have a leftover 2 here. 54, you can break it down, and at some point you'll realize that this is 27 times 2. And 27 happens to be, let's just go ahead and write it. 27 happens to be 3 times 3 times 3. So that is 3 cubed times 2. Cube root of 3 cubed. This comes out as a 3. The 2 stays inside. But because we have like terms, 2 times the cube root of 2 plus 3 times the cube root of 2 is 5 times the cube root of 2. Just like 2x plus 3x is 5x. So there's a good reason why it's good to simplify your radicals, especially if you're going to add radicals. Now, multiplying radicals. If I multiply 2 root 6 times 5 root 21, what we could do is you can multiply the numbers on the outside, so that is 10. And for the same reason, like for example, let me just do this off to the side. If I have root 6 times root 21 and I take this back to exponents, that's 6 to the 1/2 times 21 to the 1/2. Well, if they're both raised to the 1/2, I could always do 6 times 21 to the 1/2, put them together, which is the same as just taking the square root of whatever 6 times 21 is, right? So I can multiply those together within the root. So this becomes the square root of 6 times 21. I suppose that's 126. But now here's the thing. We want to simplify this and see if there's any perfect squares in 126. So now you can break that down, but a kind of a sneaky way to do this is to go back and how did we get 126? We got that by multiplying 6, which was 2 times 3, times 21, which was 3 times 7. So 126 must be 2 times 3 times 3 times 7. And notice that there's a pair of 3's. So this is the same as 10 times the square root of 3 squared times 14. And that's going to come out as a 3, which I can multiply with the 10 to become 30 times the square root of 14. Okay. You might pause the video and see if you can multiply those together. Remember, these are cube roots. So if I multiply these together, I get 35. You'd have to be multiplying the same type of root. If you were multiplying a cube root times a square root, you can't do any of what we are just talking about. They have to be the same root. But since they are, then I can just multiply the numbers in the inside, and that becomes 24. And then we want to see if there's any perfect cubes in 24, which I can find. Okay, this is a much nicer number than 126. You might see it already, but just to follow the same strategy, 4 was 2 times 2, 6 was 2 times 3, and I'm looking for a cube. So if I join all of those 3 2's together, that's the cube root of 2 cubed times 3. So that comes out as a 2. So 35 times 2 times the cube root of 3. 35 times 2 is 70. All right. All right, this next problem, one of the most missed problems every time I give a quiz or a test on this. Root 2 plus root 10 squared, the answer is not 12. It's not 12. Now, how would somebody maybe have gotten 12? They might have said, oh, I'll just distribute the square, and that's root 2 squared plus root 10 squared. When you square a square root, it gets rid of it. But that is false, okay? Don't do that. Remember, you can only distribute an exponent if it's multiplied. If it's added, you can't just distribute the square to both of those. Instead, what we want to do is, what does it mean to square this? It means I want to multiply it by itself. So I'm going to write it like that, and it is foiling. It's exactly the same as foiling. To multiply, or you can do the vertical multiplication if you want to, either way. But if I multiply root 2 times root 2, yes, there is a 2. That's root 4, which is 2. Root 2 times root 10 is root 20. Let's leave it like that for the moment. Root 10 times root 2 is another root 20. And then root 10 times root 10 is root 100, which is 10. I can combine the 2 and the 10, so I do get 12 in my answer, but what's missing is the 2 root 20. And keep in mind that 20 is 4 times 5, and 4 is a perfect square. So if it's in the root, it's going to come out as a 2. So this is 12 plus, and there's already a 2 there, so there's going to be another 2, which we can multiply together. 12 plus 4 root 5 would be the simplified answer for that. All right, one final thing with square roots. There's another thing that you get asked to do with square roots, and it's called rationalizing the denominator. That's a weird phrase. What does that mean? Essentially, what it means is we need to remove the square root from the denominator. Remove radicals from the denominator. Okay. So, and now that also may seem like, why do we care? 1 over root 3, the root 3 is not an issue. I don't have any perfect squares in there. If I wanted to get a decimal approximation of that, I could plug it into a calculator, no big deal. So why do we ask students to do this? There are some reasons when you go to calculus why it would be good to rationalize your denominator. But by and large, again, this is another thing that when you get to calculus, nobody's going to really care if you leave your answer as 1 over root 3. But we're not in calculus yet, so we want to make sure we still know how to do that. There is sort of a reason, though, why you would want to do this. And it kind of goes back to the days before calculators. If you wanted to divide 1 divided by root 3, what you would have to do, so we'll get back to this problem in a second. If you wanted to do 1 divided by root 3, now I always use an example, say you worked for NASA back in the 50s, and you needed to know what this decimal was really, really accurately to like 5 decimal places. Well, what you would have to do, they did have people worked out square roots and they had tables of them so they could look them up even before calculators. And root 3 is about 1.73205. So imagine what you would have to do if you wanted to figure out what this was really, really accurately. You would have to divide 1.73205 into 1. Now think about that division, right? You know how this works. If you've got more numbers here, you have to add a bunch of numbers, enough zeros so that you could divide 173,205 into a number, right? This is ugly. This is very ugly. You wouldn't want to do that. But instead, if you rationalize the denominator, and now let's talk about how you do that. To get rid of the square root, we're going to multiply top and bottom by the square root of 3. I can do that because square root of 3 over square root of 3 is equal to 1. And by doing that, what I end up with is root 3 over root 3 times root 3, which is root 9, which is 3. And I don't have a square root in the denominator. Now, why is that better? If 1 over root 3 is the same as root 3 over 3, think about the division problem we're faced with now. Root 3 is 1.73205 divided by 3. And even without a calculator, that's a much easier division problem than the one we were faced with, right? We could probably even just do it right now. 3 goes into 17, 5 times? That's 15. Subtract, that's 2. Bring down the 3. 3 goes into 23, 7 times, that's 21. Subtract, that's 2. Bring down the 2. 3 goes into 22, 7 times. That gives me a remainder of 1. And if I bring down that 5, 3 goes into that 5 times. And already, look at that. I've got 1 over root 3 accurate to 4 decimal places. I think I forgot the zero. The zero. Okay, well, to 3. I forgot to bring down the 0, so let's forget about that. But I've got it to 3 decimal places right there. So you can see the advantage of rationalizing the denominator if you didn't have a calculator. Today we have calculators very easily available, and so it is sort of outdated from that perspective. But again, there are reasons in calculus why you want to know how to rationalize the denominator. So 3 over root 6, rationalize that top and bottom by root 6, whatever that square root is. And that's going to give me 3 root 6. Root 6 over root 6 is 6. And I should make it as simple as possible. 3 over 6, I can divide 3 into 6, and that becomes 2. So I get root 6 over 2. Now, of course, you can't divide the 2 and the 6, right? The 6 is inside the square root. This is not, doesn't have a square root. The 6 is protected. You can't divide the 2 into the 6, so you'll have to leave it like that. And then lastly, same goal. We want to try to get rid of the square root in the denominator, but if I have an expression like this, 8 over root 5 plus 1, you probably can see, I'm going to do this off to the side, that if I just multiply top and bottom by root 5, I don't accomplish what needs to be done, because if I distribute this root 5 in the denominator, root 5 times root 5 is 5, but when I multiply the root 5 times the 1, I get another square root, which I don't want, right? The whole point of rationalizing is to not have this square root, so that's not going to work for us. And you couldn't see that, but now you can. Okay. So yeah, you're not going to get away with just multiplying top and bottom by the square root. So if it's something like this, the trick is we're going to multiply top and bottom by root 5 minus 1. And this is called the conjugate of root 5 plus 1. The conjugate of an expression like this is just changing the sign in the middle. These are conjugates. Now, let's see why that works. Of course, we can distribute if we want to. So that's 8 root 5 minus 8. Maybe I should have held off on that, but that's okay. Now look what happens if I FOIL out the inside. Root 5 times root 5 is 5. Root 5 times negative 1 is negative root 5. Positive 1 times root 5 is positive root 5. And 1 times negative 1 is negative 1. So the reason this works is you end up getting a negative root 5 and a positive root 5, which subtract out. And I'm going to have a denominator of 4. And now you may see that maybe it might be better, rather than distributing the 8 here, what if I factored it back out or left it back as just 8 times root 5 minus 1? I could reduce this even further, because now 8 over 4 is just 2. I could leave this as 2 times root 5 minus 1. And last one here. So anytime you have a fraction where it's a root minus something, or even 2 roots minus each other or added, if there's 2 terms in there, what you want to do is multiply by the conjugate, which is again the same thing here. You're just going to change the sign. Notice on this one, my original denominator was plus, so I multiply by root 5 minus 1. This one is root 7 minus root 3, so I'm going to multiply top and bottom by root 7 plus root 3. Okay, let's do the denominator first. Root 7 times root 7 is 7. Root 7 times root 3 is root 21. Negative root 3 times root 7 is negative root 21. And negative root 3 times positive root 3 is negative 3. And the root 21s cancel. And if you know that, you know every time you do the conjugate, the middle terms are going to cancel out. You can just really just do the root 7 times root 7 and this one times this one. So now I'm seeing what I'm left with in the denominator is 4, which means it's better for me not to distribute the 12 in, because I could reduce that down. 4 goes into 12. 3 times. So this is going to be 3 times root 7 plus root 3. Distributing the 3 is optional. You don't have to do that. I would leave it like that. Of course, this was the same thing up here, but all right. Hopefully this makes sense. Let me know if you have questions.